So this is the lab you're doing this week. You know what's happening. To drop the magnet to the coil, and you know what to do. One thing I haven't mentioned, just in case, is how graphs of magnetic flux and EMF related backwards. Well, we know that that graph of the flux, the slope, well, negative slope times -1, represents the actual instantaneous value of EMF. However, we know that graphs in physics are related both ways. For example, remember in PY105 you've learned that if velocity equals the slope of the graph of displacement as a function of time, displacement is related to the area of the graph or velocity as a function of time. And the same relationship works for these two graphs. So since induced EMF equals, well, -1 times the slope of this graph, we can read it backwards. We can say that this area of the graph for the EMF is supposed to be equal to, well, because of this minus, change in the flux. Well, sometimes you can use these two, for example, to compare two areas, the area on the right and the area on the left. Well, they're supposed to be equal to each other because, for example, this total area is supposed to be equal to this value minus that value. Now that value is 0. So this area is supposed to be equal to this value, well, minus this value. So same again. The shape, of course, might change. Magnet actually falling faster and faster. So this graph should not be symmetrical in your lab. However, well, the areas should be equal. And we've seen these graphs already, and now I actually have the data for this. When the loop is traveling through magnetic field, we can apply the pictorial method, before, after, to oppose. When the flux changes, the induced EMF presents. The flux doesn't change. Now here, the flux stops changing, and the flux stays the same, no induced EMF. And today, we'll learn another way to analyze this situation. And here, just another examples of problems you could, well, practice at home. This is not a problem, this is just an illustration of one of the possible applications of Faraday's law. Last week, when we were answering a question to a pre-session assignment, you mentioned this device. Well, when I young, this flashlight, you can see the LED shining up. Well, because there is a magnet inside and a coil. And with the capacitor, if I actually jump it long enough, I can charge up the capacitor, and then I can release all that electrical energy. So what is happening is basically I'm transferring my mechanical energy into electrical energy. Well, you can play with this during the lecture. Something to do. And remember, one of the examples we talked about is the ring traveling in a magnetic field. When magnetic field is uniform, which means the same in magnitude and direction everywhere, the flux doesn't change, there is no induced current. However, when the magnetic field is different, that means flux changes and there is induced current in the loop. Or we also said there's another way to look at it. We could say, okay, since magnetic field is different, the force acting on electrons is different in different places. So net force is not zero, and that net force results in a current. We don't have to have a loop. We can just have a bar. And you're supposed to see this bar already in the movie. So I'm not going to ask you this question, because you know the answer to this question. I'm going to ask you a different question. That one. Brand new question for you. What do you think about the direction of the induced electric field inside that rod? This is the rod. This one. That's the magnet. So I can move this rod in a magnetic field. You know there is a force acting on each electron from magnetic field, and one end of that rod is supposed to be positively charged, another end of that rod is supposed to be negatively charged, and we know the potential difference is related to the direction of the electric field. So, what do you think is the direction of electric field? Someone answered a different question. Again, this is the question I was looking for the answer to. Not this one. This question has only two possible answers. Well, again, this is not something completely new to us. We know that if we apply the right-hand rule, we can figure out the direction of the force acting on the charges moving in the magnetic field. Well, what do I have here? Well, a galvanometer, aluminum rod, two wires. We know how this galvanometer works. We know if this terminal is connected to a positive terminal of a battery, the deflection should go to the right. It's just a fact. It's how it's made. So I want, well, first of all, I want to make this to the right, which means I want to have this end positive the charge, plus, which means I want to move all the electrons toward this end. And if I have, well, electrons collected here, and if I have deficiency of electrons here, plus, minus, the direction of the electric field should be from plus to minus in this situation. We'll talk about that in a minute. So, but first, how should I move it and how should I keep it? How should I hold it to make this end being positively charged? Well, that's the magnet. Red means north. So magnetic field lines point in this direction. So if, let's say, if I move it down, this will be the direction of the velocity of the electrons. Down, field. So in this situation, the thumb shows the force acting on fictional positive charges. Well, electrons will be collecting, moving toward this end. This is supposed to be positive. The deflection should go to the right. And it does. And of course, if now I change the direction of the velocity, I'm supposed to change the direction of the capacitor and longer generate electricity, connected to a computer, for example. If I switch at the end, what's going to happen now? Well, now I have to switch the direction of the deflection again. So, left, right, left, right. This still, when I held it like that, this end was negative, this end was positive. If I hold it like this, this end is negative, this end is positive. Connection is different. Now, in a situation here, the rod is traveling to the right, the magnetic field is into the screen. If we apply the right-hand rule, fictional positive charges should go to the top, and electrons go down, plus, minus. Electric field should point down from plus to minus, from a higher potential to a lower potential. And now, if we knew the potential difference, we could calculate the electric field inside. Well, if we knew electric field inside, we could calculate the potential difference. Electric field is balanced. Well, if we keep the velocity constant, eventually electric field generates force which is supposed to be balanced with the force provided by magnetic field. If we just start moving, initially, the magnetic field generates stronger force. That leads to separation of charges. But if we keep moving, eventually, a specific amount of electrons getting collected here, and a stable equilibrium situation is reached finally. And in that situation, two forces acting on each electron, from magnetic field, from electric field. But since equilibrium is reached, net force is supposed to be equal to 0. When two forces equal to each other, we can cancel the charge, and that gives the value for electric field or for potential difference across the ends. And well, we have to remember this particular calculation has been done for a situation when all elements, the rod, the magnetic field, the velocity, has been perpendicular to each other. What if it's not the case? Well, in that case, as we know, parallel components don't do anything. So we just can exclude parallel components out of the picture. We just have to use a perpendicular component of velocity and a perpendicular component of the magnetic field, and that will give you a result. And you did, well, you saw, and you did this problem when doing the precession quiz. It's a Boeing 747 flying, and here, well, we can calculate the potential difference across the ends of the wing. Here in this situation, magnetic field again points into the screen, velocity points up, so fictional positive charges would be moving to the left, electrons actually moving to the right. So we have potential difference, high potential, low potential, electric field generated across the wing points to the right. This is my second question to you. Let's say we have three rods like that. How would you rank the induced EMF in this situation? it should be voice activated. Just start talking and turn it on. Brand new business idea for someone. Well, so first of all, if we look at this one, the velocity doesn't have any parallel component. The velocity, it doesn't have any perpendicular component. The velocity is parallel to the rod, so there is no induced EMF in this rod at all. And these two rods have same length. However, this one travels twice faster. That means the induced EMF number 2 is supposed to be twice the induced EMF number 1. So 2, 1, 3. Very good. Of course, you have the answer here too. And again, that's a picture you've seen already. It's one of two problems commonly related to motional EMF. Well, that EMF, which is induced in a rod when it's moving through a magnetic field, we call motional, not emotional, just motional EMF. Now, here, you know that when the rod is moving, I'm not going to ask you this question. Velocity, magnetic field, the thumb shows you the positive end. In that case, in this situation, this rod just equals to a battery, and the direction of this current would be counterclockwise, like in a regular circuit with a battery in it. And sometimes it's actually easier to think in terms of the batteries than in terms of the pictures. Of course, before and after approach will give you the same result. But you have to draw before, after, to use the right-hand rule, so it just takes more time. If you look at this moving rod in terms of the battery, it gives you the answer a little bit faster. And I'm going to go back to this. Here, the same square coil moving through the magnetic field. Instead of thinking in terms of the changing flux, now we can think in terms of the batteries. When the loop is outside of the magnetic field, there is no induced EMF anywhere, no batteries, no current. When the loop is partially inside. So, in this situation, we can think of this side as a battery, and we observe the current. When the loop is completely inside, both sides now act like batteries. So we have two batteries, and they cancel each other out, and etc., etc. Sometimes this approach gives you a faster way to think through a problem. Now here, of course, if the rod is moving, it generates EMF, so if we have some device, we can calculate the current. It's a very, very typical problem. First question. This is the question I'm going to ask you. So the rod is initially at rest. When I take my hand, grab the rod, and start moving it. Which do you think free-body diagram is correct for that situation, for t equals 0? Number 1 or number 2? not completely evenly split, but close. When we just start the motion, in this situation, well, nothing happens instantly if there is some resistance. And in this situation, valve provides some resistance. So, as we know, it takes some time to reach the new equilibrium. So, initially, when we just start the motion, only the force from magnetic field acting on, only the force from the hand acting on the rod is involved. It takes some time for the rod to reach some specific value of EMF induced in it. That EMF generates the current. Magnetic field starts acting on the current. And only after that, after some, I don't know, microseconds, milliseconds, we have another force acting back. So at t equals 0, when we just start our motion, only hand is acting on the rod. And at slightly later time, in that situation, when we keep it moving, two forces now acting. One from our hand, and second, from magnetic field acting on the current in that rod. And of course, well, when two forces cancel each other out, the net force is 0, acceleration is 0, the rod is moving with constant velocity. For that velocity, the name is terminal velocity. It's a similar situation you studied in 105 class. If you had released an object from relatively high altitude, at first it's traveling faster and faster and faster, but eventually force of gravity is balanced up with force of air friction. Terminal velocity is reached, and after that it's traveling with a constant velocity. A similar situation. So when terminal velocity is reached, the net force is 0. And the net force is 0, that means two forces have the same magnitude. And if we know that magnitudes, well, we know everything. For example, in this problem, we know the length of the rod, we know the resistance of the whole circuit, magnetic field, and well, we know that eventually when terminal velocity is reached, the current in the circuit is 2 amps. And we would have to calculate, for example, terminal velocity. We would have to calculate the force applied to the rod by our hand, and that force is 0. Or we could calculate the force applied on the rod from magnetic field, which is supposed to be equal to the external force. How would we do that? This is how we could calculate the induced EMF. We can apply Ohm's law. Current, resistance, EMF. Related. If we know EMF, we can apply expression for motional EMF and calculate the speed. Since, well, forces are equal to each other, the force applied by a person is supposed to be equal to the force applied by a magnetic field. This is Ampere's law. Current, length of the wire. A wire is a rod now, magnetic field. That's how it works. Well, so this completes basically a problem related to moving a rod acting like a battery with no additional sources in the circuit. That's important. This circuit has only one source of EMF, this moving rod. Another situation, well, if we change the direction, we change the polarity, we change the direction of the current, however, all the calculations remain the same. This is actually one of the examples. We don't push or don't pull the rod by our hand. What do? Well, here, in this problem, there is a force of gravity acting on the rod. However, if you read the problem, the speed remains constant, which means that now the equilibrium is reached and the magnetic force, Ampere's force, has the same magnitude as the force of gravity. So as long as we set it, the rest of the problem is completely similar to the problem we just had solved. Again, there's an induced EMF, which is supposed to be also related to a current and resistance. And this force from magnetic field is supposed to be equal to, well, current, length, magnetic field, everything is mutually perpendicular, angle is 0, sine of 0 is 1. And if you apply all equations and carry out all the calculations, you get some number. Of course, we're supposed to, well, in real life, these rails are supposed to be really long. Yeah. This is a very different situation from we just had talked about a minute ago. Now, you can see there is additional source of EMF in the circuit. Now you can see a battery, an actual battery. So what's going to be happening now? Well, again, we have to separate two different times. T equals 0 and some long time after, well, the switch is closed. If we just close the switch, what's happening? Well, the current is traveling through the circuit, including the bar. Magnetic field is acting on a wire with a current. There is magnetic force, Ampere's force. This is what's happening at t equals 0. Only one force is applied to it. Well, that means there's some acceleration, so the bar starts moving faster and faster. And well, if it starts moving, that means now inside the bar, additional EMF is induced. So after, well, it starts moving, this circuit becomes equivalent with two battery circuits. Okay. And that battery generates a current in opposite direction. And eventually, the new, well, final terminal velocity is reached. Eventually, acceleration is 0. Eventually, two forces acting on this rod cancel each other out. And when that happens, again, we can calculate that final value for terminal velocity. All we have to do is just apply all laws straightforwardly to the situation. So here, initial velocity is 0, initial time is 0. The current in the circuit is equal to EMF over resistance, and this is the value of the force acting on the rod. Here, well, sometimes it might confuse people. This is the current in the circuit. This expression now gives you the current generated by this battery only. The moving rod is also a battery. And when the terminal velocity is reached, the EMF of the induced EMF has exactly the same value as the EMF of the battery has. So now, the EMF also generates current. And the current generated by induced EMF has the same magnitude but opposite direction. So there is no current in the circuit anymore. So actual current in the circuit is 0. That's why there is no net force happening. Well, however, if we need, we can relate, for example, the resistance, velocity, the EMF of the battery. induced EMF, which is supposed to be equal to this one. We just have to remember the difference between two cases. Case number one, there is no battery, only rod generates EMF. Case number two, there is an external battery, so the circuit is a little bit more complicated. We've seen this experiment. Yeah, this monster is just a big brother of this little magnet. And these big pendulum, again, just a larger copy of this small one. So we know what's supposed to happen when I use a plastic pendulum, which is not a conductor, so I cannot generate any current inside. It's moving back and forth, and magnetic field doesn't affect its motion. However, if I take a large copper plate, which is actually really heavy, it makes it stop practically immediately. It cannot get through. Well, you know why it's happening. Yeah, we can explain this, well, in terms of Faraday's law and Ampere's force. No flux, a lot of flux, as long as it induces current, right? And this magnetic field exerts a force on those currents, and we know that, well, for example, law of conservation of energy tells us you can't make it move faster, otherwise it will be moving faster and faster and faster and faster, that's just impossible. So it must make it moving slower. Actually, it stops. So we can use this phenomenon. It actually has a name. The currents generated in a plate like that we call eddy currents. And we can, well, this picture shows how the force stopping this plate is generated by a magnetic field. We can see that eddy current is actually so strong that one of the applications of those currents is making brakes in trains, for example. And this is just an example. Of course, in actual train, we don't use this huge magnet. Instead, we just use two small, much smaller electromagnets, but that's how they work. We turn on electric field generates magnetic field, and suppose this is a wheel, and the induced currents interact with external magnetic field generated by electromagnets, and the train stops. And the question was, if we switch the direction of the current in electromagnets, does it mean that the train would be moving faster and faster? Of course not. It's still going to be moving slower. And finally, generating electricity. Again, you answered one of the perception quizzes. How can we make use of generating? There are many, many different devices we can use. Someone suggested flash drive like that. Yes, flash light like that. It has a generator inside. Basically, it's a device which transmits mechanical energy into electrical energy, actually into the light eventually. Or this one. I have to work really hard. Where do I aim? Here. Well, that's how it works, basically. Again, a lot of mechanical energy we can transmit into electrical energy. And how does the generator work? Well, what we know is how a motor works. Yeah. Basically, all we have to do, we have to apply a torque from magnetic field to a loop with a current like this. And now we know that we can use the same exactly setup to transfer energy back from mechanical from electrical. Here, well, it's actually much easier. A generator, there is a loop which rotates in a magnetic field, and since the flux constantly changes, it generates a current. Well, what do you think is this? A generator or a motor? Well, it looks like this, so probably it's a generator. However, there is no difference basically between a motor and a generator. Instead of using this as a generator, I can apply potential difference to this one. And now, this is a generator, this is a motor. This is a generator, this is a motor. So, from a point of view of how we made it, there is no difference between a motor and a generator. From a point of view how we explain it, well, there is some difference. So we can stop here. When the loop rotates, the flux changes with time. When the flux changes with time, we know that the slope is related to EMF. EMF over resistance gives the current. And if we look at these two graphs again, we can see that suppose slope curve. We can see, for example, that when the flux is zero, the current is at its maximum, and when the current is zero, the flux is at its maximum. Because of the Faraday's law, actually. You saw it in the movie. This applet shows you how we actually take electricity of the rotating loop. So one end, another end, and connect it to some wires. And the current generated by a rotating loop or a coil always changes over time. So we call it alternating current or AC. A battery generates direct current or DC, which is constant with time. And all we need to know now is one more expression, which tells us how to calculate the maximum EMF or the maximum current induced by a generator. Again, this is not a completely new expression. You saw something like that in PY106 when you were talking about oscillation. So the flux depends on the orientation. So this angle changes. Rotational motion could be described in terms of angular velocity. So the angular displacement equals angular velocity times time. And if we want to calculate now the EMF induced in one single loop, what we have to calculate is this change in the flux over time. And if you have a coil with n turns, we just have to multiply by the number of turns. And it turns out that direct calculation of this expression gives the sign. Well, technically, it doesn't have to be always cosine for the flux, but it's just the most common assumption. It's just because it's up to us how to choose the initial instant t equals 0. And we can choose it when the flux is at its maximum. And start measuring time from that instant. And in that case, we always can, well, run again the same calculation. Sine has its maximum value equals 1. So the induced EMF cannot be larger than this product, right? And technically, this expression doesn't depend on the initial phase, the initial orientation of the loop. It doesn't have to be at the maximum flux, it could be at the minimum, doesn't matter. This expression is always the same. So this expression, this product, angular velocity, number of turns, magnetic field, and area of the loop, gives the value for the maximum EMF generated by the generator. However, 60 volts or 120 volts, we use, you know, on a power outlet. Do you think it's the maximum value of that EMF? No, because it changes, constantly changes. To describe, well, let's say some reasonable value. People don't use maximum values. People use maximum value divided by square root of 2. Well, there's a reason for that. So if it says 120, that means maximum value will be 120 times square root of 2. The name for this is root mean square value, RMS. And another thing to remember is how angular velocity might be related to other variables. Well, that's from PY105 class, but just in case. If you know the period, yeah, it's how much time it takes to make one complete revolution. In that case, the angular velocity equals 2 pi divided by the period, or 2 pi times a regular frequency. So in our regular standard power outlet, frequency is 60 Hz. So for our standard power outlet, the angular frequency would be 2 times pi times 60. Well, and the last thing I wanted to mention today is a transformer. This is how it looks like. A little thing like that. It has 2 coils. And of course, if you want to change a voltage or a current, these coils are supposed to have different number of turns. In my transformer, this coil has 800 turns, this coil has 1600 turns. So, and this coil is connected to a generator, and this coil, well, connected to nothing. I just measure voltage across that coil. And if I look at the numbers, so this generator gives about 5 volts, and what we see is, well, let's say about 8. Well, ideally, this voltage would be exactly twice higher than this voltage. But of course, in real life, we have always a loss of everything. In this particular situation, for example, not all magnetic field is concentrated inside this. Actually, if I open this transformer, we can see the voltage drops. Why? Because now magnetic field, which is generated by this coil, doesn't go completely in that coil. So this flux is much lower now than this flux. I have to close it back to increase the flux traveling through the secondary coil. But still, of course, there is some loss. So that's why it's not exactly twice higher than this. But of course, all our problems are going to be related to ideal transformers. And for any ideal transformer, you always can write these expressions. Number one, the Faraday's law. If we apply the Faraday's law to a single loop, that means for any coil, this ratio is supposed to be equal. Voltage over number of turns. And another one. Ideal transformer, no loss of energy. Power generated in the secondary coil is supposed to be equal to the power generated in the primary coil. And that's it. That explains all possible situations related to transformers. Thank you very much. It's exactly 8:50. I'm not holding you up.